Please, Giuseppe.
Okay, first of all, I would like to thank the organizers and Laura for organizing this session. It's nice to see you all. And today I want to talk about diffusion processes with jumps, in particular Jakobi process, and now these processes can be useful in the neuronal modeling. This is a joint work with Pierre Paty and Laura Sacerdote. Okay, so this is the kind of conference where I don't have to explain what a neuron is and how it works. So I also had very nice introduction by Ryota. Thank you for his introduction on the leaky integrated fire model. So for me, it's much easier now. So I just have to explain how I intend to model the activity of a single neuron. Okay, for me, the voltage will be a stochastic process. And this is the time evolution of my stochastic process, and I'm looking for the distribution of the spikes. Okay, this is my main goal. And from the mathematical point of view, how the model works. The voltage is a stochastic process that evolves in the presence of a threshold. Consider here constant threshold. And the neuron receives excitatory and inhibitory input. And as soon as the stochastic process touches this threshold, we have an action potential. So we have one of these spikes. So the dynamic in this model, we assume that after the spike, the stochastic process is reset instantaneously to the starting position, and the dynamic starts anew. So I don't have refractory period here, and all the interspike intervals, so the time between the spikes, are independent and identically distributed, and they all distribute as this random variable t, so the first passage time. So I will focus on the first passage time problem for this kind of processes. Okay, I defined roughly how the model works. I said I want to use a stochastic process, but which stochastic process should I use? Okay, I will start with the classical case, no, the leak integrated fire in its easiest form. So we have that the voltage of the membrane potential, so the membrane potential evolves in time according to this differential equation. So we have that tau here is the membrane time constant, and at some random times, described by Poisson process, n of E and of I, there is an excitatory or an inhibitory input that will increase or decrease the voltage of an amount delta. Okay, so in this framework, you can assume that the jump amplitudes, so these inputs, so this delta are small enough, and the frequency of these inputs is very high, and we can take a diffusion limit. Okay, long story, very short. And the diffusion equation we obtain is an SDE of this kind, and the process describing the voltage now is this process Y, that is an Ornstein-Uhlenbeck process. This is a very nice process because it's for its mathematical tractability. It has been used for decades. The literature on this process is huge. There are results on the first passage times, but this process has many drawbacks, my point of view. So there are many missing features in this model. So first of all, the Ornstein-Uhlenbeck process has unlimited state space. It means that we are describing some physical quantity with some quantity that can take infinitely large values. That this is not possible. Moreover, the changes in the voltage should depend on the actual state of the voltage, and this is not taken into account by the Ornstein-Uhlenbeck process. Moreover, we don't take into account the geometry of the neuron, and we are assuming that all the inputs are small and the frequency is very large. Okay. We want to overcome some of these features, and for instance, we can start from the first two. That's why the Jacobi process is used, was proposed by Lansky and Smith, and then by Massimiliano Tamborrino, Pat Lansky, and I. So how this process looks like? It's a diffusion process again, and here I wrote it through is infinitesimal generator. The reason why I use this notation will be clear later. It's just that this is a Markov process. So I can define it using this infinitesimal generator. What is important to understand is that this part will account from the drift part, the equation, okay? And this is the part of the diffusion. So we see now that the diffusion part, that's the part describing the noisy part, depends on the state of the process. We see X. Moreover, we still have two processes that describe the arrival of excitatory and inhibitory inputs. But now we consider that the increment or the decrement of the voltage will depend on the actual state of the process. Okay, so this is the second feature we were looking for. And moreover, we observe that the state space of the Jacobi process is limited. Okay, the state space is VI, VE, where VI and VE are the reversal potential. So the inhibitory reversal potential and the excitatory reversal potential. Okay, so the first two features we were looking for are satisfied. And of course, we prefer to rewrite everything. We want to rescale everything in 0, 1, just to simplify the notation. Okay, so this is the Jacobi process that I will call the classical Jacobi process throughout the talk. I want to stress that I will devote half of my presentation just on the motivation, and then in the end I will show the results. Okay, so we have this process and that we investigated these two papers. But going back to the first slide, my question was to analyze the first passage time problem for this process. Okay, so the best would be have the density or the distribution of T. We don't have it, unfortunately, in the case of the Jacobi process, or if you want the Wright-Fisher process, it's often also called Wright-Fisher, it's not known in a closed form. Okay, there is no analytical expression for the first passage time of the Jacobi process. So if you don't have the density, what you can try to do is to find the Laplace transform of the density. Why? Because if you have the Laplace transform, first of all, you can try to invert it. And unfortunately, you cannot do it in this case analytically. So no chance to invert this expression. But if you have the expression, you can find information on the tail of the distribution, or you can derive this expression and try to find information on the moments of the density of this first passage time. Okay, so for the Jacobi process, what I call classical Jacobi process, the Laplace transform of the first passage time is known to be a ratio of two Gaussian hypergeometric functions. Please remember these two functions because they will come back later. Okay, so it's a ratio of two hypergeometric functions. We cannot invert it, but we can derive it. Okay, we can derive it. We obtained, for instance, the first three moments. In particular, here I wrote the first moment that we are interested in because I'm using, according also what Green Jim said before, we are interested in the instantaneous firing rate. And here we are using the definition that is the reciprocal of the first moment of the first passage time. Okay, so the instantaneous firing rate is 1 over this quantity. Okay, so this is a quantity of interest. We also found information on the variance. We evaluated and we found coherence, resonance, some the contribution of inhibitory inputs, many nice results on this process we have obtained. But if we go back to the first slide, we see that something is still missing. And I want to add something more. Imagine you want to account for external factors, like, I don't know, the neuron under study, the individual under study is under pharmacological treatment, or it's under drug or alcohol consumption. So you want to account for large external factors, for instance. How can we introduce also these features in our model? That's the reason why we propose to use a Jacobi process with jumps. Okay, so these jumps are different from the other jumps. These are more large jumps and are state-dependent jumps because we want to keep the second feature again, also with the jumps. So what is the process we are thinking of? The process we are thinking of is this one. Again, I'm writing it using the infinitesimal generator. We proved that it's a Markov process, so we can do it. And unfortunately, it's the only way, it's the best way to show it. Because if I try to write an SDE whose solution is this one, it's very unpleasant to read. Okay, it's not intuitive at all. I prefer to use the infinitesimal generator. So this new process that we call non-local process or Jacobi process with jumps, the generator is like this. So you have a term that is exactly the generator of the classical Jacobi, and we have jumps. Okay, the jumps are according to a measure pi. What is important to understand now is qualitative behavior of this process. So first of all, I want to stress that the jumps are state dependent, both in the frequency, because x is here, and in the size here. So what happens? That if x, so here the process is rescaled in 0, 1. Okay, so if x approaches 0, so the lower boundary, then the frequency of the jumps increases. So we have a lot of jumps, but the amplitude of the jumps becomes smaller and smaller. So we have a lot of small jumps close to the lower boundary. If we are close to the upper boundary, well, we have less jumps, but the size of the jumps depends on the measure pi. Okay, so if pi is a measure that has a lot of mass around 0, then we will have mostly small jumps. If pi is a measure that has mass also for high values, we will have also large jumps. In any way, the jumps here are only downward, and then I will explain why. And even if the jump is large, it will never go below 0, okay? Never go below the inhibitory reversal potential. Why downward jumps? Because we had in mind this application to the pharmacological treatment, or we will see at the end that also maybe adaptation can be treated in this way. So imagine now that we have downward jumps and are state dependent. And with this plot, we should understand even better how the dynamic works. So here we have possible trajectory of this Jacobi process with jumps, and here we adjust the count of the jumps. Okay, so here we have the first jump, and we see that there is a downward jump here that is pretty large. Here another jump, another downward jump. Here in this plot, the lower boundary is -10, you see here, and the upper boundary is 100. So we see that if we go closer to the lower boundary, the number of jumps is increasing. So we have a lot of jumps, but the size of the jumps is smaller. Okay, so this is the behavior of our process. To ensure that all the dynamic will stay above the lower boundary, so it means that inhibitory reversal potential Vi is an entrance boundary, we have to pose this. It means that the drift compensate in some sense the downward jumps and the noise. Okay, so this is our very important assumption. Okay, so now before going to the main result, I need to introduce some ingredients, mathematical ingredients, and then we'll see the main result. This kind of process I defined here, this one, it's a Levy type process. And all the Levy process are defined by a triplet. So here it's this lambda. In lambda, there is the time constant, membrane time constant. Mu accounts from the input, and pi is the distribution of the jumps. Okay, so the process and his generator is described by this triplet. And there is a one-to-one correspondence between this triplet, and a Bernstein function. What is a Bernstein function? It's just a function that is a positive function, infinitely differentiable with this property. Okay, what is important to say is that if we have a Levy process, we can write a unique function, Bernstein function of this kind. Okay, so in our case, this Bernstein function will have this form. And it depends, of course, on the distribution of the jumps, pi. Okay, why these Bernstein functions are important, we will understand it later. But first, I want to stress what can we define with this function phi. This function w, here is evaluated when n is an integer number. So it's the product of this function phi. But in general, if n is not integer, we can define it as the solution of this equation. This is a function that was introduced by Paty and Savov in 2018, and it's a generalization of the gamma function. You see that from this definition that if phi n is equal to n, actually this is the definition of the gamma function. So this extends the gamma function. And using this extension of gamma function, we want to extend our Gaussian hypergeometric function. Do you remember that the Laplace transform, or the first passage time of the Jacobi process, was a ratio of two Gaussian hypergeometric functions of this kind? And that is actually, it has this expression without the w. If we add this w here, of course, it's a new function, but we call it still using this notation to phi1, phi, because if we don't have jumps, so if phi is equal to 0, we don't have jumps, actually the two functions coincide. Okay, so it's a way to generalize the Gaussian hypergeometric functions. Okay, now we have the list of all the ingredients, and we are ready to read the main result. We were looking for the first passage time of this process, and we were able to write the Laplace transform of the first passage time of the Jacobi process with jumps. And look, it's again a ratio of two functions. It's actually a ratio of two generalized Gaussian hypergeometric functions, where the function is the one that we defined here using the Paty-Savov function. Okay, this result is nice, and I just want to stress that it's not trivial. It's true that we obtained something similar to the classical case, but in some sense, we force it to look similar. No? So it's not trivial at all. I will not go into the details of the proof because it's very technical and very long. I will just want to show one step of the proof because it gives you the flavor of what's the idea behind this strategy. So the idea is to inherit all the information we know on the classical Jacobi process to the case with jumps. Okay, so we built an operator, this lambda, that will map our information that we know on the classical Jacobi process to the case of the Jacobi process with jumps. Okay, how can we build such an operator? We use a theory of Levy processes and subordinators, because in particular, lambda is defined this way. We know, I said that to a Levy process, we have a Bernstein function, a correspondence to a Bernstein function. To a Bernstein function, we have a correspondence to a subordinator. That is a stochastic process that is non-decreasing and with stationary increments. What is important so is that if we know the Bernstein function, and we know it, we are able to write it, we can obtain the subordinator. We take this integral of the subordinator, and then this will be our operator. Okay, so this operator will help us in mapping or inherit, sometimes it's called intertwining, because we have the chance to import, in some sense, information on the classical case to the Jacobi with jumps. And of course, if we know the Laplace transform, we can derive the expression and look, for instance, to the first moment of the first passage time. That's useful for the firing rate. But now let's see in a more special case, because if we we cannot say much if we do not say what is the distribution of the jumps. Okay, so we have to specify the distribution of the jumps. Here, we decided to use an exponential type density. Okay, for the jumps. If we explicit this pi, we are able to write the generator of the process, and we are able to write the Bernstein function associated to this process, okay, in a closed form. Well, since we have all this information, we can use our theorem. We know the Laplace transform, so we can derive it. We know the first moment of the first passage time, and in this case, we can write it very explicitly. I understand that formula can look cumbersome, but actually is very easy to evaluate numerically. Okay, so we can evaluate the first passage time. And for instance, what we observe that if we plot the mean first passage time, so the mean time we have to wait before the first crossing of the threshold, decreases if we increase alpha. Who is alpha? Alpha is the parameter of the density of the jumps. Why so? This is just a plot, very simple plot of the density of the exponential density when we change alpha. And we see that if alpha is large, most of the mass will be for small values. Okay, while if lambda is smaller, we will have higher mass for larger values. This means that if we consider alpha large, imagine here, if alpha is large, most of the jumps that are downward jumps will be very small. So if the process is close to the threshold, even if we have small jumps, the small jumps close to the threshold are rare. But if they are also small, we will have that we don't have wait too much before the crossing. Whether if we are close to the threshold and we have a large downward jumps, we are increasing a lot the time before the first spike. Okay, so this is not surprising according to our framework. What is maybe more surprising is this plot here. In this plot, we have the firing rate of the classical Jacobi case. So it's a firing rate as a function of excitatory inputs. Okay, this is the rate of excitatory inputs. So in the case blue solid line, we have the classical Jacobi, and the dashed red line is our Jacobi with jumps. We see that first of all, the firing rate of our case is always smaller. And okay, this is not surprising because we are introducing inhibition from outside. Okay, we are downward jumps. So we are trying to stop or to decrease the activity of the neuron. So this is something that we wanted. So it's okay, we obtained it. But I want to stress that there's another feature here. If we don't have refractory period, if we consider a leaky integrated fire, here it's a Jacobi, but also in other cases, the firing rate increases linearly and unboundedly. Okay, and this is not very reasonable. Whether in our case we have that the firing rate saturates. Okay, so it's you can think that is a it's adaptation or whatever you want, but it's true that in this case we observe that a saturation of the firing rate. That's something that's a feature that it's nice. I want to stress that here in this plot I used exponential distribution of the jumps, but this model has high freedom in the choice of the distribution of the jumps. Okay, if you want to model different things, you just have to change the distribution of the jumps. Okay, so there is high degree of freedom, but of course this is just a first investigation. We need to add upward jumps, and we need to investigate higher moments of the first passage time, and so on, and to see how to choose the density in different cases, in different situations we want to model. Okay, so there are many other open problems, but I'm running out of time, I think. So I would like to thank my co-authors, and I would like to thank you for your attention.
Thank you, Giuseppe. Are there questions or comments?
It was a really nice talk.
Thank you, Rinci.
Questions?
Short question, okay?
Sure.
So is it possible, or why it is difficult to incorporate the excitation instead of inhibition?
Okay, it's very nice.
Difficult technically?
Yes, it's difficult from a mathematical point of view. There are two reasons. One is on the property of this measure that is in the in the integral. So the jumps, the distribution of the jumps, it needs to have some properties, and also we want that the crossing of the threshold, we want that this for the diffusion, not for the jumps. We want to cross the threshold due to the diffusion, and we don't want to have the hitting time, or we don't want to overcome the threshold with a jump. Okay, so that's the main difficulty, and we are trying to fix it and see how we can
yes,
manage
because
it.
I think in biologically there is a report about the very large EPSP.
Okay.
So maybe taking into account of a large jump can be also biologically important problem. Just a comment.
Okay, thank you. Yeah, definitely we are planning to. It just from the mathematical point of view, it gave us some issues.
Even approximately, I think it's very important. Thank you.
Thank you.
Yeah, sorry. Ciao Giuseppe. One question I have is you were mentioning that I don't remember anymore. Okay, I need to get that question back.
You're getting old, Massimo.
Yeah. I mean that's a skipping lunch. That's a consequence. Okay. So you were mentioning that you don't want to cross the threshold due to the jumps. What's the reason for that?
Because it's in that case, this expression, I think it's this expression is not exactly this one. We should take into account we have troubles in mainly the technical part of our proof. So we need to cross it in with the diffusion, not with the jumps, because we lose some regularity of all this function of this operator that are involved in the proof.
Okay, because well, I mean, perhaps one can try to condition it on that and distinguish between the two cases, depending on. I mean, if you know the time when the jump occurs, then this might give you some sort of probability confidence on whether you are going to cross for that or not.
Yes, yeah, definitely. I believe it's possible. I'm not saying it's not possible. Just we have to fix something, but maybe, as you said, there will be two components here or something. We have to distinguish between the two cases, or we can at least start with very small upward jumps. I don't know. We'll still have to fix it.
Okay. Yeah, I mean, if the possibility might be to allow the jumps to have the same amplitude as the possible upward oscillation of the process, right? So if you go from time t to times t plus 1, and you know that the Jacobi has a possible jump amplitude of that size, and you ask the jump to be of that size, then it might work.
Yeah, actually, it's possible, because here we impose that the downward jump is always smaller than x minus vi. So we never jump below the lower boundary. So maybe we can impose that it never jumps above the threshold, going upwards.
But in any case, we have only downward jumps.
Here, yes.
So you cannot have a crossing due to the jumps.
No, here, yes, but he's saying if we try to extend it.
Okay, to positive jumps.
Yeah.
Okay, I think it's time to close this session.